Welcome everyone. So this is our 121st live stream geometry. We have 4 people here with us now, and today I'm going to go over 3 problems from the Turkey team selection test and other problems from the Iranian Geometry Olympiad and 1 from Korea. So we'll see how far we get. I think they're pretty hard problems. So if you want to join us in the future, feel free to email me at mgreenv801@gmail.com. It's in the description of my video. We meet every Sunday at 8 a.m. US Central Time. All right, so I will get started. Everyone see my screen? So here is the first problem. It's from a Turkey team selection test. So Yusuf sent me this. So thanks, Yusuf. Yeah, I took all the problems he sent me. So, I know you said you wouldn't be able to make it today, so yeah, if you have to drop off early, don't worry, but yeah, I appreciate it. So yeah, so we have the in circle is tangent at PE and F. So I created a tool for this. So let's call this I. All right, so X, Y, and Z are the perpendiculars from A, B, and C to some line passing through I. Okay, so I just pick any random line passing through I, and the perpendiculars are X, Y, and Z. And then we want to show that dx, EY, and FC are concurrent. This is interesting. All right, so this is going to be X, Y, and Z. Let's rename it. X, Y, and Z. So I'm going to hide a couple things. This kind of reminds me of the orthopole. So I think isn't there some idea of an orthopole where you take a random line and you take the perpendiculars from A, B, and C to that line? I think there's some idea like that.
Yes, I agree. This looks very familiar.
Yeah. So those are the 3 perpendiculars. So we would have dx, EY, and FC. So yeah, that diagram looks okay. I don't think that they shouldn't concur on AX, so let's make it look a little different. Let's see. Maybe I could have just point G also to make the figure look nicer. So yeah, it's like that. Let me try to make the best figure I can. So if I make it like a very obtuse triangle, I think it looks better when it's like a more obtuse triangle like that, or closer to obtuse. Something like that. So maybe Desargues theorem. Although let's think about that. So I think the idea of the orthopole I forget exactly what the concept of the orthopole says. I think it's the perpendicular from X to others use it. I think if we drop, let me try this. If we drop a perpendicular from X to BC, and then Y to AB, and C, or Y to AC and C to AB. Oh, I thought maybe those would concur, but they don't. Oh, Z, I mean Z to AB. Yeah, so I think that's the idea of the orthopole, that those three should concur. I don't know if that's helps us that much in showing that these three concur, but maybe it does. So I'm just going to draw on that point.
So how would we prove that?
I don't know the proof of it. I just know it's a general fact. If you have any triangle and you have any line, and I don't think it has to be a line through the incenter, and you drop perpendiculars from A, B, and C to that line, and then you take the 3 feet of the perpendiculars and you drop perpendiculars to each of the sides, then those three concur. I don't remember what the proof is. So yeah, if you can figure it out, that would be interesting. That would be nice. But yeah.
Okay.
Maybe there's something special about JH. Let's see. Yeah, I don't know if there's really that much we can do. I actually wonder, like maybe the problem can be generalized. So EX, EY, and FC. Is there any way we could use Desargues? Or maybe there's something special. Let's see, if we take this point, this point. So yeah, what happens when we move this line around? X, Y, and Z change.
I think it would be helpful to invert around the circle.
Okay. So D, E, and F would stay fixed. And A, B, and C would go to the midpoints of DF, DE, and EF, right?
Yeah, but A, B, and C are not really important.
Okay.
They aren't doing anything, except that they make that X lies on the circle AEIF.
Okay. So if we invert it about the end circle, oh. So wait, if X, so X lies on that circle, and you figured that out using inversion?
No, that is just because of 90-degree angles.
Okay. Yeah, no, you're right. So, yeah.
So, for example, X would go to the intersection of the line with EF.
Okay.
And yeah, we have to prove 3 circles of coaxial, which is worse, but I think in general the problem is nicer.
Okay. So maybe I'll delete these 3 lines at point J for now. So if we invert, that would be the same. We try to invert all 3 of those lines. So we would have dx, and then fz, and ey, and would we want to show they're coaxial, or that they all pass through a common point? Or maybe, yeah, sorry, this circle is only partly drawn. So what I should probably do is draw the whole line dx, and then reflect that. So,
well, it will be coaxial, but they have the common point, the center of inversion.
oh yeah, you're right.
Yeah.
So if we take this point, maybe there's something special about it. So yeah, I mean, it would be like, yeah, obviously we don't know point H exists yet, but it would be on that line if it did. I wonder if Fy and Ez meet at, okay. So it looks like YF and EZ meet on the end circle. That looks pretty important, it seems. So maybe that's just an angle chase. So if we know that, maybe it's like harmonics or something like that. So if YF and EZ meet on the end circle by symmetry, that would mean what would that mean by symmetry? So I mean YF and X right? There has to be some kind of symmetric condition that would hold with point X, right? So maybe X, E, and YD meet on the end circle. I think that's what it is. I think X, E, and YD meet on the end circle. And XF and ZD meet on the end circle. And I'm assuming those can all be angle chased. And then maybe it's like Pascal's theorem or something. Not sure. So we try to see where KH meets this segment. Right, is KH and B collinear? I would be surprised. I don't know, that's not true. It's not true that KH and B are collinear. But yeah, I'm trying to think how to use harmonics. If there's a way we can do that. So, I mean, basically it's the same as saying, let's say we let EF meet this line. And I wonder if it meets on this circle. Looks like it, yeah. So EF and that line look like they meet on the circle. And basically, can we use cross ratios somehow? So
how do you define the circle?
this circle right here.
Yep.
I think it was like the inversion of I don't even remember.
Line dx. Okay.
Line
Basically, it's trivial that then the lines concur since x goes to n by the inversion.
By the inversion. Okay. So yeah, so that's kind of circular reasoning. So yeah, inversion would fix L and M. Maybe, I don't know if that's useful. And it would also fix K. And so yeah, it would fix all these points. So basically, line FK would go to the circle FIK, right? Yeah. So like, and then Y would go to this point. So yeah, it looks like this is cyclic. So yeah, we have like a lot of different circles here. So that would be cyclic, and what other lines have we drawn? So this would be cyclic, and this would be cyclic. So yeah, we would have a lot of circles passing through point N.
Can you draw a line ML?
ML?
Yeah.
Whoops, sorry.
No, like not a segment line, I mean.
Yeah, that was my bad. And that looks like it also passes through N. So yeah, there's a lot of stuff going on in this diagram. It almost looks like, so dx, it almost looks like by symmetry we'd have kx, ym, and zl concurrent. Let's see if that's true. Yeah. So there's almost like a symmetry here. It's kind of interesting. Maybe if we can show one, it proves the other. There's just so much going on here. All right, so let's get back to what we're trying to prove. How do we... Well, maybe if we can show... Well, if we can show that dx, I wonder if we can show that if we can show that kx, ym, and zl concur, does that prove that those concur? I don't know. Sorry. Maybe we could redefine H to just be the intersection of EY and FC. And then we could try to use Desargues. We'd have Desargues on triangle. What if we try to use Desargues on XML and DEF? So, like I define H to be this intersection, and we have triangle XML and DEF, and we try to use Desargues. That might be a little tricky. So ML and EF meet at N. Yeah, would that work? Let's see. We have to make sure everything's defined right. So I'm trying to, I'm going to try to color in those two polygons. So we'd have XML and then DEF. What if we try to use Desargues? So ML and EF meet at N, and then FD and XM meet at F, and XL and DE meet at E, and EF and N are collinear. So then that would mean that DX. Okay, now I'm confused. No, I don't think I did that right. We need triangle EY. So we need the segment EY. So maybe DEF. Yeah, no, that doesn't work. Okay, actually, so let's try this. Triangles YHZ. This might work better. So we have YHZ, and actually, no, I'm not sure about this either. DEF because then we'd want to show YE, ZF, and DH concur. And then O, we know, like, we probably could show that.
What about on DYZ and XEF?
EYZ and XEF. Okay. So EF and YZ need an N. And then yeah, maybe that's the way to do it. I kind of like that. Yeah, does that just like solve it once we've proven the points are in the right place? Maybe it does. So yeah, we have to show. Yeah, it depends how we define point N, but I wonder if that's, yeah, the way to do it. Okay, so I think that might work. We just have to start from the beginning and figure out how we want to define everything. So do we want to let N be the intersection of EF with YZ? Do we want to define it that way? Do we want to define it using inversion? I'm not sure yet. So I guess, is it obvious that EF? So first, I think we want to show that L and M lie in the circle, right? And then once we do that, how do we show that these three concur?
I think that L is the reflection of F over that line.
Oh, L is a reflection of F. Okay.
Yeah. So if you can prove that, then it's basically done.
Interesting. So we could define L and M that way, right?
No, I think that we can define that to be the intersection of the two segments, and we can prove it like on the circle using angle chase, but I don't know how to prove the reflection yet.
Well, if we did define it to be the reflection, I mean, basically, this is a line passing through the center of the circle. So, like, we would know, oh, I see.
Isn't it obvious that it is reflection, also angle chase?
Yeah, I think it should just
Oh,
be
yeah.
angle chase.
Yeah, I think it's obvious.
So then that proves that these concur at some point N.
Yeah, and
So I could hide some of the circles. Once we know that, then we just apply Desargues. So I don't even know if we need inversion then. Trying to see. So do we even need, like, yeah, maybe the solution is much simpler. Like, maybe we just You just have to use the Desargues, and we don't need conversion or yeah, I don't know. Let's see. So yeah, let's first. So first we show the existence of L and M, or that they meet like that. Then it's obvious that these concur at point N. And then if we use the Desargues on these two triangles, really we would just say since N, L, and M concur, then dx, ey, and fz have to concur. Is that true? Does that argument work? Seems okay to me, right?
Yeah.
Okay. All right, so let's write it up. Let me see if I could make more room for the solution. So shrink it just a tiny bit. I think that should be enough room for the solution. So okay, so let L and M be the reflection of E and F over the line through I. Or so the reflections of E and F over L. But what is O? I don't even remember what O is anymore. Let's see. Yeah, I'll just hide it. So I'm just thinking what the angle chase is to show that EX and L are collinear. So we'd have to show that angle YXL is EXC, right? I mean, it's the same as showing that angle FXY is angle EXZ. And that's because this is cyclic, right? So we do want this circle right here. So EXI and FIX or FXY would be FAI, which would be EAI, which would be EXI. So that proves it. Okay. So we can start by saying angle AXI equals AFI equals AEI equals 90. I'll just write it out faster. So since angle AXI equals 90, then AFXIE is cyclic. And let L and M be the reflection of E and F over L. All right. So we have angle angle LXY is FXY is FAI. FAI, which should be angle EAI, which EAI is angle EXI. That means that L, X, and E are collinear. And then similarly, fx and m are linear. So by symmetry, EF, L, and LM concur at a point N. And then by Desargues' theorem on dyz and xcf, that solves the problem. That solves the problem. So dx, dy, and fz concur since n, L, and M concur. All right. So we had to use that I as the incenter because that meant that this is cyclic, and that helped a lot with the angle chasing. But I believe this works. I don't see any issues here. All right, so let's move on to the next one. Nice solution. So yeah, that was kind of an elegant problem. We have three circles on the same side of the line L. So that omega 1 and omega 2 are tangent at K and L. And they're also tangent to gamma at M and N. Okay, so maybe inversion would make this easy. This seems like it might be an inversion problem. So let's see. So let's do it like this. So we have some two circles that are tangent to the line, and they're both tangent to another circle, but I don't know if that circle is tangent to the line. So let's think about this. We want some other circle, so they're tangent at K and L. And tangent to some other circle at M and N. How do we draw that other circle? Looks like someone else is joining. So what if I were to just like try to eyeball it? Let me just try to understand. What? So hey Raymond, thanks for joining. So yeah, good to see you. So yeah, if I just try to guess the figure right now, so these two circles don't intersect and they're not the same size. We have a circle passing through K and L, and it intersects this circle at A and B. So let's call this A and this B. So we already had A and B, so those are going to be renamed. For now, I just want to understand the problem better. So then we reflect M and N over L. So this would be M, and this would be N. Something like right here. I didn't draw an exact diagram. And then we reflect those over L. And we want to show that A, B, and those 2 points are cyclic. So get this and this. Obviously, these are an isosceles trapezoid. So yeah, it looks true. Although it's kind of hard to tell because the figure is not exact. So okay. So yeah, if you guys can think of how to draw an exact figure, let me know. So this would be R and S. Oops. This would be R. And this would be S.
Well, I think it is easy to draw it. You just start with the circle in the middle.
Oh, you just start with this, and then you draw two circles tangent, and then you draw the line tangent, and then everything goes from there.
Yeah.
Okay. All right. So let's do that. So we have this circle. And two other circles. Let me draw the tangent line. Let me see if I can make the tangent line more horizontal. Maybe like that. Okay. So that would be this would be K and L. And then we have a circle passing through K and L. This would be A and B. And then we reflect M and N. And that should be R and S. We'll just draw this isosceles trapezoid to make it more obvious. Call this O. Oops. And we want to show that ABRS cyclic. Looks a little bit like the power ratio lemma. Although we would need another circle in that case. Well, no, actually we have the two circles already, so. But yeah, I wonder if the power ratio lemma makes it easier.
I think this problem is just trivial.
Oh, really?
Yeah. Just you just spam 2, 3 radical axes and that's it.
Oh, really? Okay.
Looks like to me. So first you would have to show that KMNL is cyclic, which looks true, and I believe it is just angle chase.
Yeah. It looks easy. And it looks like R and then R and S would lie on. Well,
That is not true in general.
it's not true in general that R and S would lie on it. Oh, yeah.
Yeah.
Okay.
But because of the reflection, you have also that KLRS is cyclic.
Okay. KLRS would be cyclic.
Yeah.
Let me try to draw it so yeah, R and S don't lie in the circle. So then we would have K, L, R, and S is cyclic.
Yeah. And then you can firstly use radical axis. Actually, no. Mn, Kl, and Rs are concurrent.
Okay.
That is because Mn and Rs are reflections about the line Kl.
Okay. So that's just by symmetry.
Yeah. And then if you do radical axis theorem on the circle KMNL,
Okay.
the circle in the middle, the center O circle, and also that and circle AB LK,
Okay.
then AB also passes through the same point.
Okay. So then it's
And-
just power of a point.
Yeah.
Okay. So this is a pretty easy problem. Just a little bit of angle chasing pretty much. All right.
At least I think this is correct.
Let's see. So let me just try to make the diagram a little bit easier. So let's see if I make EL. I want to make one of these. Let's see. So yeah, if I move it like that, and then I make DM smaller, then it looks a little easier. Okay. So that will just give me more room to write the proof. Something like that. So step one, so we know that MN, RS, and KL meet at point C, and then CD and E would be collinear also. So let's think about that. So so step one is showing that MNLK is cyclic. And let's think about that. That feels like it's just an angle chase, like you said. So we want to calculate angle KMN. So that would be 180 minus DMK minus OMN. And we'd want to show we'd want to show DKM plus OMN is NLK. When NLK is 90 minus NLE. So that should be an angle chase. Let me write it on paper. One sec. Just a second. right, so you have angle DMK plus angle OMN. We want to show that equals angle NLK. But NLK, that's going to be 90 minus angle NLE. Which is 90 minus NLE is half of NEL. And NEL, DMK is DKM. So DKM is going to be 90 minus half of maybe it's best to drop a perpendicular from O to KL. That might make the angle chase a little easier, I think. Let's do that. Yeah, there might be an easier way to see this that I'm just not seeing right away, but it should be bashable. Let's see. Yeah, we will do stuff with powers once we show that this is cyclic right here. So hold on just a moment. So DKM and then OMN. So OMN is 90 minus half of MON. And DKM so DKM is going to be 90 minus half of ODK. And so it just the problem reduces to showing that ODK plus MON equals NEL, or something like that with directed angles. No. It reduces to showing. I think it reduces to showing that ODK plus OEL plus MON is 360. Yeah. Is that obvious? It should be. Yeah, because if you look at this whole pentagon, basically, yeah, this angle plus this angle plus this angle should be 360. Okay, so KLNM. So yeah, we don't need point F. Use 3 variables. Yeah. So I'll do it like this. So we have angle DKM plus angle OMN is equal to angle 2 plus MON over 2. And then we also have angle NLK is equal to angle MEL over 2. Okay. Yeah, because it's tangent. So actually, there's probably so angle DKM is 90 minus. Well, actually, I'll just leave it like this. But then, so we have ODK, MON, and NEL. Those add up to 360. So that implies that DK, these two are equal. So actually, I'll write it like this. So this is 180 minus KMN. So I wanted to do it on a separate line, but see if it works this time. Yeah, there we go. Perfect. All right. So basically we want to show that this is equal to this, but it's true because it's not hard to show that those three add up to 360. So angle ODK plus angle MON plus angle NEL is equal to 360. And that would mean that equal to angle NLK. Using the above equations. And that implies that that's cyclic. So that implies that KMNL is cyclic. And then we want to show that this is cyclic. So first we use the radical axis theorem to show. So we have this circle. We'll do that later. First, we want to show that DE, MN, and KL concur, right? The circle KLAB have a name. They don't say what the name is, and they don't give it a name, but I can just write it out, KLAB. So for KLRS, I forget, how do we know that that's cyclic? Is that just, yeah, it's all about doing things in the right order here, it looks like. So okay, so by symmetry, these three, that's what I was missing, is we turn the diagram sideways, so I got confused. So I think step one is showing that these concur. That's true by symmetry, right? Then we want to show that, do we even need that CD and E are collinear? I don't know if we need that. So we just start showing these are collinear, and then the radical axis theorem says that AB, MN, and KL would concur at C. But then we first need to show that this is cyclic. So let me see if I remember how to do that.
Just symmetry, because R and S are a reflection of M and N.
Oh, over K and L. So if K, M, and L is cyclic, yeah, you're right. Okay. So by symmetry, by reflecting over L, K, R, S, L is cyclic. Okay. And then by symmetry, Mn, Rs, and Kl concur to point C. And by the radical axis theorem, A, B, Mn, and Kl concur. So I could write out what the circles are. So by the radical axis theorem, first I'll say what concurs, then I'll see if I can write the circles. So A, B, Mn, and Rl concur at C. So it's the radical axis theorem on ABMN, KLRS, and what's the other circle? ABMN, KLRS, and MNKL. This for ABMN should be. All right, ABMN, MNKL, and I think it's actually ABKL. So I don't think this one's right. Let me think about that. So I think it should be ABMN and KL. I think that's right. And then once you know that, then it's just power of a point. So then we would have CA times CB equals CM times CN equals CR times CS. ABRS is cyclic. All right. Yes, exactly. Let's move on to the next problem. But yeah, this one was pretty easy. I agree.